Hello, everyone. Thank you for coming to our December online lecture event. We are the Center for Climate Science and Engineering at the University of Toronto. We host monthly guest lectures. My name is Mohamed Jalair. I'm the CSE manager. Today, we are pleased to feature Dr. Kirk Kernelson from the Ontario Power Generation. First of all, I'd like to go through the land acknowledgement. We wish to acknowledge this land on which the University of Toronto operates. For thousands of years, it has been the traditional land of the Huron-Wendat, the Seneca, and the Mississaugas of the Credit. Today, this meeting place is still home to many Indigenous people from across the Turtle Island, and very grateful to have the opportunity to work on this land. For those who haven't attended our guest lecture events before, we are the Center for Climate Science and Engineering, which is a research and education center within the Civil and Mineral Engineering Department at the University of Toronto, and it was established in 2019. The CSE is made up of a multidisciplinary team of faculty members participating together in interdisciplinary research at the intersection of climate science and engineering. Our center's director is Oya Marjan, and she focuses on structural analysis. Marianne Atsipolo focuses on transportation. Paul Kushner looks at climate dynamics. Graham Norrell, Professor Emeritus, focuses on health and process safety. Daniel Poston looks at life cycle assessment. Karen Smith works on atmospheric science. Marianne Tucci focuses on building science. Sam Markov from the University of California, Merced, focuses on sustainability and resilience. And then me, the CSE manager. So one of the key activities that CSE doing is education around climate science and engineering. There are two graduate courses that have been developed and run at the University of Toronto. 8 online learning modules were developed and are available for use in Ontario higher education environments. Secondly, our faculty members are carrying out research projects in collaboration at the intersection of climate science and engineering. Also, our team is arranging outreach activities just like this one, where we invite the public or university people to give a presentation about topics that are aligned with the mandate and vision we have at the center. Now, I'd like to introduce today's guest lecture speaker, Dr. Kirk Kernelson, as the Director of Environment and Climate Change at Ontario Power Generation, OPG, oversees vital environmental initiatives and plays a pivotal role in advancing the company's climate change plan. With a doctoral degree from McMaster University School of Earth, Environment, and Society, where he also serves as an adjunct assistant professor, Dr. Kennelson is well versed in the complexities of climate change, hydrology, and machine learning applications. His extensive body of work includes numerous peer-reviewed journal articles, reports, and industry guidance. As a leader, he supervises a skilled team of engineers and energy experts steering the development of OPG's multifaceted climate change plan. Dr. Kernelson also co-chairs the CSA Technical Committee on Climate Change Adaptation of Dams and has a rich background spanning research, operations, and regulatory processes. This includes serving on the Ottawa River Regulation Planning Board, actively participating in the International Joint Commission's Great Lakes boards and committees, and previously advancing OPG's water resources and hydrology program as the senior manager of water resources. He is going to give a presentation on climate change from the trenches, adaptation and mitigation in the electricity sector. Dr. Kernelson, welcome. Thank you for being here today. We are very excited to learn more about your presentation. Now the floor is yours.
Okay, let's see. Okay, it works. Great. Yeah, I'm really excited to be here to talk to everyone about calling it climate change from the trenches. So really talk about some of the different studies, the work that we've done over the past few years with some of our partners, looking at climate change, adaptation, mitigation, some of the challenges that we face as the electricity sector as we move forward towards, ultimately decarbonizing our economy and managing this this thing that we call climate change, the threat of climate change to our society. And so just to get started, a little bit of background on Ontario Power Generation. For those that don't know, Ontario is actually not considered to be a vertically integrated electricity system. And what that means is we have different agencies that are responsible for generation, for transmission and distribution of electricity, as well as for the management of the Ontario grid. So in OPG's particular case, we're a power generator, but we don't control the electricity grid. And there's other partners such as the Hydro One that actually helps us get the electricity that we produced into the market and towards our consumers. And so there is a difference with other, particularly provinces that you might be familiar with, for example, Hydro-Quebec or Manitoba Hydro as our neighbors, which are vertically integrated. So those companies do manage the entirety of their electrical system. Within OPG, we have a large fleet. We have two nuclear stations. We also have leased nuclear stations at Bruce. We have two thermal sites in OPG proper, as well as 4 combined cycle gas generators at our Atura subsidiary. We have 1 solar facility, 66 hydroelectric generating stations that belong to OPG proper, and in the last few years, we've also taken on a United States subsidiary called Eagle Creek Power, which has 85 small hydro generating stations distributed, as you can see here on this map, throughout the United States. So we have a fairly broad portfolio of generation, both within and outside of Ontario, that we're looking at advancing and growing, but also that we are trying to understand what are all the climate change impacts on this wide fleet in very different areas. From a corporate perspective, one of my responsibilities is as the steward of OPG's climate plan. And we have 2 primary goals that are part of that plan. Is number 1, to be a net zero company by 2040, and that's speaking to our operations. But the other one is to be a catalyst for a net zero economy by 2050. So we want to see economy-wide decarbonization. And what does that mean for OPG to be participating in that broader process? And largely, it means us understanding how is our fleet going to operate in the electricity sector of the future, and how can we help other aspects, other players within our economy to decarbonize their operations. So, for example, transportation, heavy industry, those sorts of groups, because they're going to also rely on a functioning, effective, affordable electricity system. And so I've talked a little bit about our existing fleet, but there's also a lot of work that's going on for looking to the future. We have a number of key climate change initiatives that we're taking on as a company. And I'm not going to be able to talk about all of these in great detail. But number 1 is we're looking at being a global leader, one of the first in developing small modular reactor technologies. We're looking at refurbishments of our existing nuclear power plants so that they're going to continue to operate well into the future. We're looking at investing in new hydropower generation in Ontario. We have subsidiaries, one is Ivy and the other one is Power On, that are around broader electrification. So Ivy focuses on vehicle charging stations, and Power On actually looks at a bigger picture at fleet electrification. So for example, helping to electrify the TTC buses and helping to electrify some of the ferries that we have in Ontario. We're also looking into various other aspects to expand our business, battery storage. We're actively pursuing hydrogen development. We're focusing on building the resiliency of our current assets because they are going to have to continue to operate into the future, and thinking more broadly about our impact on the planet. For example, looking at things like nature-based solutions and our biodiversity program, which is very well established. We're actually, I think, on track to be planting, I believe it's 5 million trees in the next couple of years we'll have completed. Before we dig into some of the previous case studies, though, it is important to set a baseline understanding of what is important in the electricity system. So it is something that we all inherently know what electricity is, and we take it for granted, and we get kind of annoyed when the lights go out on us. But understanding all the things that are going on behind the scenes to keep this, machine that we call the electricity grid actually operating, because it is that. It's one of the world's biggest machines that we're operating, and it's very interconnected. And we learned that sort of the hard way in 2003, when much of the northeastern United States and Canada actually had a large-scale blackout because of issues that had happened further away on the grid. And that happens because all of our different grids are interconnected and working to constantly balance themselves out. And so a couple of key things to keep in mind for the electricity system is, number 1, for all intents and purposes, it must be in balance at all times. And that means the demand of electricity has to equal the supply. And the way that we actualize that is through an electricity market. And so we get signals from the market that tell us how much energy is needed, where it's needed, and solves the equation of how are we going to get the energy to the consumers that are demanding it at that time. So at any given point in time, as you turn on the lights, there is a corresponding increase in generation somewhere. The other key characteristics of the electricity system is reliability. And so we have very, very low tolerance for power outages. And we know that that happens in small sections and blocks with winter storms and those types of events. But on the broad scale, the last time that we had a large scale grid outage was all the way back in 2003. And so it's really important for our modern society that the grid continue to reliably function. The other thing is change. We know that our electricity system is undergoing a lot of change, and we expect to see more change in the future. In Ontario, we burned the last bit of coal for producing electricity in 2014. We also brought in a lot of what we would call intermittent renewables. So that's wind and solar, meaning they don't follow a particular signal. They're not dispatched. When the wind blows and the sun is out, they produce electricity. And what that means is there's a lot more variability in the energy system. And at OPG, we have actually seen that reflected in the way that we operate our hydro and a lot of our thermal fleet, which is able to follow the ebbs and flows of the energy system. But because of that, it means it's changed the way that we operate. We expect more of those changes now going into the future in order to be able to balance that supply and demand. So having a bit of understanding of those key characteristics, we'll also talk a little bit here about electricity system, say requirements, but also the terms that would be very native to me to be using within our industry. So the first one is going to be capacity. And what that's talking about is the amount of electricity that can be produced at any one time. And so we will often talk about what is the maximum capacity of our plants, or what's the maximum amount of energy that is required on the Ontario grid. And so one of the important things to realize and understand is that we don't use all of that capacity all the time. The grid, the generating stations are not functioning at 100%. They're following the demand. And so what's important, though, is that we do have the capacity on the grid when it's needed. So when we get to that single hottest day, hottest hour of the year, or vice versa, the very coldest day and hour of the year, there's enough energy to meet that demand. If we don't have it, what we start to see is blackouts and brownouts. And so when we're looking through this process of designing the electricity system, we're actually always designing to the extreme to make sure we don't run up against the edge and actually have to force different communities, different people off the grid in order to not exceed the capacity that we have. The second thing is generation. It's very closely tied to the first. This is what you actually pay on your electricity bill. And so the generation is the amount of electricity that's produced over a given period of time. So this is more along the lines of our supply. And so you will see we would typically measure that in megawatt hours. We use metric units. So you'll see throughout this presentation, gigawatt and terawatt hours. Mostly what you will see on your electricity bill would be kilowatt hours. So looking at that in the thousand scale. But what we do is however much capacity is being produced over a period of time, we simply aggregate that up and that gives you your megawatt hours. And so again, there's a difference between the generation that we need over the course of a year and what is that capacity that's needed in a single moment. And part of that is provided by what we would consider to be ancillaries or ancillary services that we provide to the grid. So one of those is voltage support. And so within the electricity system, you need to produce the amount of bulk electricity. You also need to make sure you have the right flow of power through all the lines and the right amount of voltage to deliver that power. And so one of those is what we call voltage support. We also have a product that we offer into the market called operating reserve. And what that means is it's an amount of generation that is not needed at the moment, but it's available in case something happens elsewhere on the grid so that it can come online quickly and backstop that capacity shortfall. So for example, if we have a lot of wind and solar, let's say we've got a very sunny, very windy day, and they're producing a couple thousand megawatts into the Ontario grid, we actually need the equivalent amount of energy standing by in case something happens. If the clouds come over and we get a sudden drop in our solar generation, or if there's a shift in the wind patterns, the other thing we keep that operating reserve for is contingency situations. So if we had a large unit's operating and something happened and that station tripped offline, whatever energy that station was producing on the market needs to get made up in a very short period of time. And so that product is called operating reserve. The other thing that we offer is what's called automatic generation control. And so this is very short-term variability. So as I said previously, we always have to balance exactly supply and demand. And what the market does is gives us, let's say, a course correction. So it will help us every couple of minutes, we'll get a new dispatch, and that tells us where our stations need to operate. But in between that, in very real time, we need to actually modify to match supply and demand. And so that's where the IESO, which is the Independent Electricity System Operator of Ontario, they're the ones that control our grid. They can actually dispatch our units in real time, and over the course of seconds, they're constantly fine-tuning the supply and demand on the grid through the units that we operate. And so those things are actually really important to understand some of these case studies, because as we change some of the requirements of the energy system and as we look at the impacts of climate change, it starts to change the equations on capacity and generation and the types of technologies that are available for us to meet these key aspects or these key requirements of the electricity system. And so what we do know is that climate change is going to impact the energy, and I should say here, the electricity sector. We've seen variable types of impacts. This is from a study we participated in by the Oranos Consortium in Quebec. And where we look at things like a freezing rain, changes in stream flow, forest fires, snow, some of these very obvious impacts, they actually impact our equipment in different ways. So we can look at the direct impact on production, physical degradation of our equipment. As a generator, can we get our product to the market? So is Hydro One being interrupted by, for example, a forest fire or freezing rain, so that our product not only can't get to our market, but that also means that some of our customers are now offline. And it also impacts demand. So as we see temperatures rising, we see subsequent increases in higher and higher demand as people have their air conditioning set higher and higher. On the other side of the coin, what we expect to see is people switch over to heat pumps or electric heating, actually a change in the demand in the winter period as we start to offset natural gas home heating with electrical-based home heating. And so all these impacts of climate change and the interactions within the electricity sector really do change the way that we think about and operate our systems. And so a lot of what we're going to be focusing on is the physical risks, which is really what you were seeing on the Oranos study, is how climate change will physically impact the electricity sector. It's also important to understand that we're going to be varied by transition risks. And so what these are defined as is the different policy drivers, the different technology that's available, our consideration of our risk tolerance as an operator, how are we going to be impacted by public safety, and also how does our social license, what we call it, how does the view of society on energy and environment and social needs vary. And so we're going to see some of these transition risks, these transitions within sort of our broader society, and how they can also impact the physical way that our stations operate. Going back a level, I want to show you a little bit about how we see the electricity system changing in terms of the supply and the demand going forward. We'll talk about some of the risks and how we meet some of that supply and demand. So the IESO, the Independent Electricity System Operator, recently produced what they call the Pathways to Decarbonization report. And what you'll see on these graphs on the right is two different lines. So one is the 2022, what's called the APO, which in our lingo is the Annual Planning Outlook. So this is something that the IESO publishes every year, forward-looking for about a decade or so, and to say, under certain assumptions, here's what the electricity system is going to look like. And in this case, they're contrasting their sort of business as usual APO with a scenario pathways that was asked for by the minister to say, what happens if we're going to get to a decarbonized economy? And so for context, this decarbonized economy is actually in line with the 1.5 degree C uh, Paris Accord agreement. So global temperatures staying to 1.5 degrees Celsius. And the International Energy Agency, that's the IEA jargon there, says that countries like Canada are going to have to be net zero by around 2040. This also aligns with Canada's nationally determined contribution, which is that our country is going to be net zero by 2050. And so we're looking at this Pathways to Decarbonization report over that time window to meet Canada's international determined targets. And so one of the things that we're looking at to actually achieve decarbonization is also the electrification of our society. And so in order for Canada, our economy as a whole, to decarbonize, what does that mean? Well, the energy that we consume has to be switched to low or non-emitting sources of energy. And the biggest one of those is electricity. And so what does that mean for all of us as energy consumers? Well, it means switching to electric vehicles. It means switching our home heating from natural gas furnaces to things like heat pumps. It means for heavy industry, switching from gas and coal furnaces and coke ovens to things like electric arc furnaces. And all of that means that the electricity demand is going to grow. And what does that mean for us as a generation company, for us as an electricity sector? It means that we need to double or triple the energy infrastructure, largely due to capacity needs, in the next 50 years. So we have to double or triple all of the electricity system that we've built out over the last 100 years or so that we've had electricity. And we need to do that within the next 50 years. And you can see on their pathway to decarbonization scenario, the top graph, I apologize, it's a little small, is the net energy demand. So that's the amount of generation that's needed. That was that second column on the previous slide. And as you can see, the electricity demand in terawatt hours is actually going to grow about twice as much as we switch to sources of energy. What's really interesting, though, is if you look at that net winter peak. So on the coldest days of the year, because we've now switched to electricity generated heat for so many homes, that peak capacity need is actually going to triple. So a lot of our cost is not necessarily in increasing the amount of bulk generation, but increasing the capacity that we need for those coldest and hottest days of the year in order to meet the short-term demand that's going to show up at those times. And we also have to do it reliably. So when we add some of those last generation sources, we need to make sure that they're dispatchable. And what that means is that they're going to turn on when we tell them to, not relying on necessarily the weather conditions that are just going to happen to be there at that day. So making sure that we have the balance with some of the wind, solar, intermittent renewables, with our more stable base of nuclear, and with some of our peaking capabilities that we have currently in hydro, as well as within our natural gas fleets. And so this is actually a challenge because the electricity system operates, I guess the academic term would be a nexus, right? We sit at this interface where we're looking from a policy perspective at competing energy, economy, environmental policies, and social policies, and the different demands that are placed on all these things. And so there's this constant, call it a tug of war, conversation that's occurring in all of these areas. So yes, we want to decarbonize, but we want to make sure that it's not done in such a way that energy becomes completely unaffordable, or we put people into electricity poverty. We also don't want to do it in a way that destroys the environment around us. So we're trying constantly to have these conversations about what is the most prudent and the effective way to balance these different impacts. And the figure that you see on the right is my rendition, coming from my particularly hydro background, of just what the Ontario water world looks like. And so you can see all the different regulators that we have to deal with, not all of them at the same time, but in different watersheds, the regulators we have, all the other users we participate with. So it's not just Ontario Power Generation that exists on our rivers. We deal with the riparians, the shippers, people that have their own needs and desires of that water system, right? We don't have exclusive access to it. And then on the far right, some of the activities that are going on as well within those watersheds. Sorry, there's just this little, all of your pictures are showing up on the right-hand side and blocking some of the slides on me. So there's a lot of different activities with which we have to work with and sometimes compete and negotiate around how we're going to use that resource that we have. So it's not a straightforward or an easy system always to manage. And it's not like we as a power producer have our sole right of way on the watersheds in which we operate. And by the way, we are happy to work with each of these groups, our regulators, the various other users within the watershed. But it's true that we're not always completely aligned, and that there's sometimes a good degree of healthy conflict in identifying just what are the best needs of those resources in the areas that we operate in. And so one of these case studies that I wanted to show, this came up a few years ago, was pressure that we see exerted by a lot of the environmental movement in certain areas. And one of those is to renaturalize river flow regimes. And so what that means is that we can store less of the natural inflow to a reservoir. And in some cases, some would advocate completely removing dams and seeing, or to have more of a natural stream flow regime. And that has impacts on electricity systems. And so this is work that we undertook as this question came up, and we were trying to explore really what does this mean to Ontario if this were to be a question that was more asked of us. And so to quantify the potential impacts, we came up with this idea of passing 80% of the natural inflow. This is on a daily basis that comes into our reservoirs. And just putting in a few, these are actually Canadian-based examples that we found in the literature to say, what does that mean to have more of a naturalized river flow regime? And so we can see what some of the literature is suggesting that might truly look like at this point. And I do want to say, as we get into this case study a little bit, we do very much pay attention to the fisheries that in the watersheds in which we operate. We pay attention to the local riparians, the stakeholders. We do have proactive and productive conversations with all those groups. So it's not like this is a negative if we can't change things. But I think it's really indicative of the type of conversation we need to be productively having, because there is no single best solution, and there's no way to produce all of this energy without having the conversations about the social, the environmental changes as well. And so I've already talked a little bit about the Ontario context for energy system, the need for balancing supply and demand. This is what this looked like actually in 2019. I picked a random warm period in the summer, and you can see the base demand on an hourly basis was around 16,000 megawatts. The peak demand here was getting up to just shy of 24,000 megawatts. This past September, I think Ontario hit a new high since 2013, which is a little over 26,000 megawatts. And so what we're seeing is the shifting of demand based on the time of day in the year. And we need to have the dispatchable resources to follow that daily peak as it goes up and down. And so hydropower is a very flexible resource that we use to meet those daily peak demands. And the base alternative that we're comparing to in this case is primarily gas and oil. So right now, natural gas is the main other dispatchable resource that we have the sort of viable technology for in Ontario. And so when we have these peak demands, when we need that capacity, if it's not being met by hydro, it's going to be met by natural gas. And so that's the comparative that we were looking at in this particular case. A little bit more context. This is actually a fairly typical operating regime for a reservoir in Ontario. Most of our reservoirs will have a seasonal cycle. This is what you're seeing coming from a regulatory instrument with the Ministry of Natural Resources and Forestry called a water management plan. So the red lines is the boundaries in which we have to operate this particular reservoir. And you can see here the different curves that are shown a couple of historic years. And this was coming out in 2019. 2018. So the blue curve was where we were at that point in 2018. A couple of things that you will see is during the winter period from January to March, that's what we would call our drawdown. And so that's where we lower the water level in the reservoir. And that has two purposes. Number one, it helps us meet some of the wintertime demand. We get a little bit of extra flow when people are heating their homes. And then it also builds space for the spring, what we call the freshet. So that's the period in the spring. The trees aren't green yet. The vegetation hasn't come out. We have a lot of snowpack on the landscape and things are starting to warm up. So the snow is melting. The ground is typically quite saturated. Usually it's a rainier time of the year, and we don't have the vegetation present to actually absorb and transpire some of that water either. And so what that means is we typically get our peak flows coming within the spring season in the province of Ontario. It's also the time when you'd be most likely to experience flooding. And so that drawdown allows our reservoir to absorb that incoming inflow and has a very strong flood mitigation aspect to it as well. Then when we get towards the summertime, later in the spring, we have minimum flow requirements for most fish will spawn in the springtime. There's a few fall spawners as well. And in the summertime, our ranges tighten up quite a bit. And actually, this one's a fairly generous range. Sometimes we'll only have the ability to move the water level 10 to 20, maybe 30 centimeters, anytime between the Victoria Day weekend and the Thanksgiving weekend, which is basically what we would call the cottage or the camp season, the recreational season in Ontario. And then after that, the boundaries increase quite a bit. In this particular case, there is also, I don't know if you can see my mouse, a little tail end just as we're getting into October, September, and that's to help us support in this particular reservoir effluent dilution. So there's water treatment plants downstream, and as we get into the summer drier period, there's a little bit of an allowance there for us to go draw the water down a little bit lower so that we can make sure that we're meeting the effluent dilution requirements that we have downstream. And so the question is now, what happens if we have to pass 80% of our inflows? And we did this similar analysis all across Ontario. And the question what we first had to wrestle with was, well, what are our priorities going to be? So do we want to keep the water level high so that it stays within the summer range? And that's going to help our riparians, boaters, other stakeholders. But you'll see there that blue curve on the left, you're not getting the winter drawdown, so we're not providing the flood protection. Or can we shift this whole curve down? We're still allowing 80% of our natural inflows to pass through. We started to look at this as the scenario of, does this provide us some flood mitigation? And as you can see, we never get to the point where we're actually refilling the reservoir. And so the answer is no. So in our analysis, we stuck with the high curve. We'll at least keep people happy in the summer and see what happens, because we're really not providing any flood mitigation in the spring either. And so what does that look like? This watershed I've actually been showing you is the Kaministiquia watershed. So the main reservoir here is Dog Lake, which is the reservoir that you're seeing in the figures. This is upstream of the city of Thunder Bay. And what happens is if we were required to pass 80% of those inflows, you can see the amount of increase that actually happens throughout Thunder Bay in the typical spring. And so in about a third of the years, we're going to have a doubling, 100 to 200% increase in the daily peak outflows, which is directly translated into potentially more flooding. And we can see that there's a lot of days that go beyond that double to triple increase. And the reason being is a lot of these communities that we have in Ontario have grown up for 100 years with reservoirs providing some level of flood protection to them every single year, as well as helping us produce more electricity. This is the backbone of Ontario's electricity system. And so we have to recognize that there's a history in the built environment of the community actually growing up this way. And there's a number of cities that we have along rivers that would be in a very similar position that we analyzed without the additional flood protection of our reservoirs. There would be at this particular point a lot of damage caused if we were to simply remove or significantly limit the drawdown profiles that have been established. But there's a broader impact to that this as well. And this is where I'm bringing forward that it's important to have this kind of conversation of the benefits and trade-offs. So by doing this, Ontario does not have the largest reservoirs in Canada. We don't have the geography for it. So where you have, for example, in British Columbia, they have large mountains, they can have much more reservoirs and supplement the depth of those reservoirs to use the water to supplement lower flow periods. Quebec similarly has a much more favorable topography. And so in Ontario, we do largely rely on our inflows most of the year. The main period where we take advantage of that storage is for our winter drawdown and our spring refill. Most of the summer, we're largely using the inflows that we have to produce hydropower. And so what we found is by actually passing 80% of the inflow from a a terawatt hour from the generation perspective, we'd only lose between 0.8 and 1.4 terawatt hours. And so that's not inconsequential, but it's not necessarily really significant compared to our base case where we're getting about 42 terawatt hours. So now by passing around 80% of inflows, we've only lost about a terawatt hour of production, which again is still certainly consequential. But what becomes important is that lost capacity. And what that means is we're actually having to supplement that with more gas generation or gas and oil on the electricity system. And so what that means is we're having about 0.4 million tons more of CO2 emitted every single year. And that equates to a direct cost of $40 to $75 million more that ratepayers would see showing up on their electricity bill. So we're now seeing this tie into some of the health, the financial, the economic benefits, but also we need to meet those peak capacities that right now that hydro can provide. So those hottest and coldest days of the year. And so not just that we have the direct cost, the $40 to $75 million, which is the cost of buying fuel versus using our hydro, you also have to add new capacity. And so we found that had a cost of around $200 million per year to build new effectively gas plants to offset the amount of hydro that's cost. And so what I'm really trying to highlight here again is that we're dealing with this constant wrestling of where do we see ourselves going as a society, of what's important to us from an energy, from an environmental, from an economic perspective, because all of these things tug at each other in different directions. And so it's a fulsome discussion that we can have. And so how do we value some of our assets? And so this is work that we did with the Uranos Consortium. You can find this guidebook. I've got the little QR code here. You can go back and scan it, and you can find this guidebook. We operate at a regulated business, but this guidebook talks about various ways that we can value hydropower and the energy that we produce. And so for us, what's important is that we can look at the impacts of climate change. We can look at our hydro assets that we have. We need to make sure as a regulated business that we're making prudent decision making for our ratepayers. So we go through in front of a group called the Ontario Energy Board, and they're the ones that set our rates. And primarily they want to make sure that we're making good decisions for ratepayers, that we're not becoming too expensive, and to sort of put a check and balance on OPG given the size that we are in the market. And so within this guide, you'll see that there's a lot of very complicated ways that we can actually value different types of assets, in this case, hydropower. So depending whether we're looking for actual financial decision making, looking at financial disclosures, different ways that we'd be looking at different business activities. So are we building something new? Are we upgrading? Are we refurbishing something? And it also comes down to how are we getting paid and compensated? What is giving us the signal to do that building? And so in many cases, in OPG's perspective, we're actually looking, if we're going through this from our guided decision-making process through either project development or upgrades, we then look through our fair value proposition. And typically that we're looking then income-based. So we're looking at our revenues and the amount of energy that we can produce versus the cost of producing that energy in different ways. And so that's ultimately what we use to justify the business cases that we have. But even that energy production can actually be impacted by climate change in a number of ways. On the hydro side, for example, you'd look at changing stream flows, high or low. You would also then look at the impacts of extreme events. Things like air temperature change our demand, and that changes how much energy we produce, also changes the market value. If we're looking at the market value of electricity, changes with supply and demand. So all these things come together to help us develop the business case and how we value some of our assets. And so when we worked on this particular case study, I think we provided at a fairly high level, but a lot of the climate data, we rely on our partners at the Uranos Consortium. They are the climate change experts that we use. We develop our own in-house water system models, and we worked with Uranos to develop an economic valuation model looking at climate change. And so we considered two different baselines, because this is a really important even discussion as we're thinking forward with climate change, is what's the right thing to compare against? So we consider to be the hydrologic baseline we take historic water conditions and we pass them through our energy model to figure out how much value we're going to get. So how much electricity are we going to produce from that water? But when we're looking at climate change, we have to be careful. Are we producing a like-for-like comparison? And so when we talk about our climatological baseline, what we are looking at in that case is if we took those climate models and we use the historic period of time that is present in those models, and we use that same model all the way through into the future. So what we're comparing is historic modeled values versus future modeled values. And then we have a bit more of a like-for-like comparison, and we can start looking at the differences so that we can tease out some of the nuances of what is modeled error versus a signal that we're seeing. And this was actually a very interesting case study for us. So I apologize to all the sort of the academics online. We're not going to get into the big nuances of the model that we've generated and all the steps that we followed. For the purposes here, though, let's assume that we have a well-calibrated model, which we did, and that we validated it, which we did. But I'm not going to show all of those results today. But we had a fit-for-purpose model. One of the key lessons that we learned was we had to be very consistent in the model calibration and the climate change data that we used. We found we could introduce biases by starting to swap out things like the precipitation data set. So if I used one historic value to calibrate my model, then I started to use a very different data set to do my bias correction, my downscaling, my climate model, we could actually get very different results. And so even that itself was an important lesson, because that's actually fairly common way for people to operate some of these models, to just take something that they had and just apply a different scenario to it. And so effectively the model becomes conditioned on the data that's used. We also ended up with a very, at first, perplexing problem. And so when we were looking at how we measure our data, we're starting to see that average annual inflows really weren't changing. And so, okay, that's good for us from a climate change perspective. But we found that electricity production was decreasing. And that's counterintuitive on the hydro side, because we expect if we have constant inflows, and sometimes we've even found increasing inflows, why would we be losing energy? And so we had to dig into this particular problem. And if there's any other hydrologists listening in, you'll be very familiar with this flow duration curve. But what we see on the x-axis is the exceedance probability. So that is the probability that the water flow is going to be above a certain level. So median flow being the 50th percentile. As we get into the higher exceedance, what this is saying is that we are most often exceeding that certain value. So we can see 100% of the time we're exceeding zero. Approximately 25 or 75%, 80% of the time we're exceeding here around 25 CMS. 60% of the time we're exceeding around 45 CMS, so on and so forth. And we can see we only exceed these very high flows a very small percentage of the time. And so what we found was actually happening is a very subtle change coming about by climate change, but we're seeing from the blue down to the red, actually a decrease in our low flow days. So your typical day, the flow is actually decreasing. And on our high flow days, we're actually getting a few more high flow days. And so what that means is, even though our median here at the 50th percentile is staying the same, more low flow days mean less production. More high flow days, those are happening in the spring periods, and we don't build our hydro stations to capture every last quantum of water. It's not economical. And so that results in spilled water. So in the end, we were actually potentially losing a little bit of production due to climate change. Very interesting result to anyone with a business background. We were also starting to look at this from a business case perspective, is what is going to be the impact of that change in production with different discount rates? And so what we do in the business world is we apply discount rates so that we can take our investments and we can compare them in the net present value. And the basic idea being value that we derived in the future is not worth the same amount of value that is derived today. So effectively, this is depreciating the value of the energy that we are producing at this particular site. And so what you can see, and actually just one more for the non-financial people, effectively, this is the exact opposite of interest, right? So interest, where you'd see that growth, depreciation, you would see sort of the decrease in the value of the asset. But it brings us back to the net present value. And we're looking here at various climate scenarios. So this is from a model ensemble with different RCP is the representative concentration pathways. So 4.5 being our emissions peak around 2040, and that's more or less the time we hit net zero. RCP 8.5 being they would consider quote unquote business as usual, but continue increasing emissions out to the end of the century. What you can see is as we apply the discount rate, the value of that energy in my current net present value starts to decrease. And so with a higher discount rate, it decreases a lot faster. And what that means is I'm paying more attention to what is going to be happening at, say, 6% between now and 2050 than what I am towards the end of the life of the asset. In the case of hydro, we're assuming 90 years or beyond. Whereas a lower discount rate means we're taking a longer term perspective on the value that we're getting from that asset. What's also really interesting from a business as climate change perspective is the impact that this has on uncertainty. And so as you can see, the uncertainty band shrinks with a higher discount rate, meaning it becomes less and less important how uncertain of a decision I'm making into the future. So with a high discount rate, I'm also less concerned about the variability in the future because I'm assuming that effectively I will have money to deal with any changes that are needed in the future. And so not only is there a play on climate change and the physical impacts of our assets, there's also an impact of inherently climate change on the way that we do our financial valuations. And this becomes really important because some of the financing decisions that we have to make, and as we're looking at climate change, can be very expensive. And so this next case study, also done with Oranos, as well as partners at Hydro-Quebec, Manitoba Hydro, Rio Tinto, a number of others, we were looking at how do we deal with flood frequency analysis for dam safety. So in OPG, we're very proud to have an industry-leading dam safety program overall. And I want to highlight, dams are designed to be extremely safe under very extreme events. But those extreme events also carry a lot of uncertainty. So you might be used to thinking about something like a 1 in 100 year flood. Well, in the dam safety world, 1 in 100 is the very lowest. And that basically only applies to a dam that if it were to fail and be breached, no one would notice the difference. Most of our dams are well beyond what we consider to be a 1 in 1,000, where this one was tied to the Quebec dam safety regulation of 1 in 10,000 year flood. And some of our dams are even beyond that. But just highlighting, even in this case, it's a synthetic example that Oranos presented with known data, just depending on how you sample it, you can see how much variability you get in that extreme, this 99th percentile. And that difference of 1,500 to 2,500 cubic meters per second for us as a design event on a dam could represent tens, if not hundreds of millions of dollars of investment that we'd have to put in to meet certain dam safety regulations. So it's really important for us to not only understand the uncertainty in estimating these extreme events, but the impact of climate change on them as well. And I'm going to go through this very quickly now for the sake of time, but we had several working groups that were done as part of this project. One, a fairly simple conservative estimate, which is working group 1, looking at a variety of different climate models, getting down into working group 2, which had a much more comprehensive treatment of all the uncertainty that they could actually get into their hands and quantify as part of this work. And just an example here, we had the findings of that in terms of the percent change, and you can see some of our different climate models actually even disagreed on the direction that this design event would be changing. And so they varied by model, the findings varied by estimation uncertainty, and this becomes a key challenge for us sort of down in the trenches, hundreds of millions of dollars of decision, and we have to make good decisions because we can only build one dam, right? You can't build it for uncertain conditions, and so we have to make some cost benefit trade-offs and lower the risks as much as reasonably possible. And so these are my last slide in a bit. How are we going to get there? What's the OPG perspective? We want to apply a bit of a paradigm shift. So historically, vulnerability and risk studies, in my experience, not this OPG experience, but when I've asked people around, they don't tend to result in a lot of action. We see a lot of organizations that will undertake a broad risk study. They get a series of recommendations. They might take one or two off the top, but the rest tend to sit on the shelves. The other thing is we have to be prudent to our ratepayers. So we don't want to just undertake climate change projects. We want to make sure something reaches the end of its life and focus on building it back better to address climate change. And so we want to do that by embedding it into our core processes. So it's going to become a way of life. It's going to be integrated into our asset management cycle. But the thing that we need to do and equip our staff to do is to think a little bit differently about decision making. And one of those is we're going to look to embrace a series of techniques, and you can research some of these on your own, called decision making under deep uncertainty. And so here's just a sample textbook, for example, that is freely available online, but looks at how do you address uncertainty in some of the design decisions, because that's not necessarily a common thing that we would do in the engineering world, even though we are happy with the uncertainty, for example, in our financial investments. It's a type of uncertainty we're much more comfortable with. How do we take some of that thinking and apply it to the work that we do in a way that is also going to be respectful of the costs that we have to pay, recognizing we need to make a lot of investments to build that capacity to get to a net zero grid. And that is the end of the presentation. So I would just want to say again, thank you very much for having me here. It was a pleasure. I think we're going to go into some Q&A.